Hello, in this video I would like to give a short introduction to linear algebra. Let me start from very simple equation. Solve Ix equal to b. Let's denote by 1, where a and b are real numbers, okay? So how to solve this equation? We don't know a and b yet, right? So basically, some students might tell me, yes, we just divide both sides of 1 by a, and we get x equal to b over a. But is it correct? Unfortunately, this is not correct. We can divide by a if a is not 0, right? So we still have the case when a equal to 0. Don't forget that. So we need to consider at least two cases. The first case, when a is not 0, and you can divide both sides of 1 by a, and you get a unique solution of 1, okay? The second case, when a is 0. And in this situation, 1 becomes 0 equal to b. So we still need to consider two sub-cases, right? If b is equal to 0, any x can be a solution of the equation 1. That means 1 has infinitely many solutions. Right? And when b is not 0, of course 1 does not have any solution. So I just, write in short, no solution, right? Because, if b is different to 0, so this equation, of course, does not have any solution, is it? So even very simple equation 1, Ax equal to b, we still need to consider three cases, okay? That is about linear equation in one variable. Now let's consider another linear equation. Ax plus by equal to c. Again, a, b, c are real numbers. Okay? So how do you think? It seems like this is the equation of a straight line. Is it correct? It's what we learned from pre-calculus. Straight line. And of course, on any straight line, there are infinitely many points. That means there are infinitely many pairs of x and y, right, satisfying this equation. But that is just the first feeling. And again, that is wrong. Or I can say, yeah, that is not enough. Why? Because if you have the case a equal to b equal to 0 and c is not 0, so no solution. You see, it's pretty interesting, right? Of course, if I give you concrete numbers a and b and c, you think yes, you might decide no solution or infinitely many solutions. And in case if just one number a or b is different to 0, of course, you are good. Make sense? You are good because that is equation of a straight line. So infinitely many solutions. All right, so this is just two examples, right, about linear equations. Of course, you might have linear equations in many variables, x, y, z, t, whatever you want, right? And coefficients a and b and c are just numbers, right? Real numbers. And sometimes, if you look at this equation as an equation of some straight line, I mean, in that case, right, we are in this situation, when one of A and B is different to 0. So we have an equation of a straight line, and suppose that you have another equation of another straight line, right? Let's say you have a1x plus b1y equal to c1. This is another straight line. So a natural question is, do these straight lines intersect with each other? Right? So we want to see if they intersect with each other or not. So that means we need to find the intersection, right? Intersection. And of course, from geometry, you might think, and that, if you have two straight lines, we might have three situations. The first situation, two straight lines intersect at only one point. So in this case, unique solution, right? The second case, two straight lines do not intersect, but parallel. That means they have the same slope, right? Parallel. In this case, no solution. And the last case is that two straight lines are the same. So they are the same. They have intersection and they have the same slope. So I can write just they are the same, right? Just with different colors. In this situation, how many solutions? Infinitely many solutions. Right? And then, how to write the question to find the intersection of two straight lines. So I can write in the following way. I need to find all pairs x, y such that x, y satisfy pole equations, meaning ax plus by equal to c and a1x plus b1y equal to c1. All pairs of x and y satisfying these two equations at the same time. So in this situation, we have a system of linear equations. You see, this is a system of linear equation of LA. Okay, so sometimes if you have a system of linear equations in two variables, you might think, yeah, we need to find intersections, right, of two straight lines. And of course, since linear equations may be in many variables, so you have system of linear equations in many variables. Okay, but this is just a very simple example. Now look at this. That's what we are talking about, system of linear equation, right? And in this situation, x and y are variables. X and y are repeated in pole equations. But if the system is very huge one, means there are a lot of equations and there are a lot of variables. So it's not convenient, right, to write the whole system each time. Does that make sense? All right, so I try to find another language how to rewrite our system right here. Okay, how to rewrite this system. But I would like to give you a very concrete example, okay, so that we can feel that better. Just take some numbers. Let's consider the following system. X plus y equal to 1 and 2x minus y equal to 3. All right, so x and y are repeated. I want to rewrite in another form. Now let's consider the first equation. I have x plus y equal to 1, right? I look at the coefficients of this equation. I say, yeah, actually this is 1 times x plus 1 times y equal to 1, right? And if you look at the second equation from this point of view, you might think, yeah, we have 2 times x plus, minus 1 times y equal to 3. Okay? So you might think, yeah, there is a pair 1 and 1 in here and another pair 2 and 1 in here, not 1, negative 1, right? And there's some multiplication in this situation, right? A pair 1, 1 and product with x and y. The pair 2, negative 1 and then product with x and y. Does that make sense? So, yeah, let's think about that. I say, yeah, let's do this. I just want to write a pair 1 and 1 and multiply with x and y, right? Another pair and say this is equal to 1. You know, I just write that very naively, okay? And I have another one. 2 negative 1 times x and y, right? And equal to 3. Agree? And now I see, yeah, x and y are repeated. So, you know, somehow we may just don't write them, right? So I can write in the following way. I say, yeah, this is 1, 1. The first pair, the second pair is 2, negative 1, right? And then I multiply with, okay, let's say this, x and y, okay? And then this equal to, since this is 1 and 3. Maybe that is not very convenient, right? But, you know, that is just my logic, okay? So, but I think it is not very good denotion. Why? Because, you know, here I have 2 rows. In the first table, I have 2 rows and 2 columns, right? And here I have just 1 row and 2 columns, right? X and Y, right? 2 columns. And here we have 1 row and 2 columns. So it seems like, yeah, it's not good at all. Right? You have 2 times 2, and then you times with 1 times 2, and you get something like 1 times 2. You know, yeah, I think it's not good, right? So let me just rewrite it in the following form. And probably that makes more sense, right, to me. So I write 1, 1, 2, negative 1, x and y in here. So that means I rewrite this row as a column, right? Equal to 1, 3. So I have, this is 2 times 2, and here 2 times 1. Finally, I get 2 times 1. Why? Because, you know, it's interesting. Because, you know, I have 2 times 2 right here, right? And here 2 times 1. So I can multiply these two guys, right? Because they have the same, you see, 1 and 1, and then x and y. Is that correct? And then finally I get this. So I may think, yes, it seems, you know, good to me. 1 and 1 multiply with this guy, right? Such that 1 with the x and then this one with the y. So I may define some product in here. All right. Okay. Now it looks good to me. Now I want to rewrite the original system in this form. So I have 1, 1, 2, negative 1. Let me repeat this. X, y equal to 1, 3. And let's denote this by A. This is by X capital and this is by B. So I can rewrite my system in the form of linear equation. Ix equal to B. You see, that's what we start from the beginning of this lecture. Ix equal to B. And if you have a system of linear equations, right? For example, in this case, you still can rewrite that system in the form of Ix equal to B. So from here, it seems like we have 3 cases. The first case, the system does not have solution. Maybe, okay, does not have solution. Maybe has only one solution. Or maybe has infinitely many solutions. Right? You see, you know, it's very interesting, right? And of course, you can use the same approach to any system of linear equations in any number of variables. Okay, so this is very, very interesting. All right, now I already have some product in here. Okay, I have some product in here. Let me rewrite ax equal to b. And now, I don't care about the number of equations and the number of variables in the system of linear equation. I always can rewrite in this form. So I need to analyze, such system, okay? And of course, in this situation, we already defined some product, right? We have some operation in here. This multiplication, but this is not, like scalar multiplication. We call such tables, such arrays, matrices. Okay, so we have a matrix multiplication in this case. You see, we go from numbers, right? From numbers to matrices. That means to arrays. So now we deal with arrays. You see, this is matrix A. This is matrix B. No, X. And this is matrix B. And you may determine the size of the matrix. Like in this case, you have two by two because you have 2 rows and 2 columns, right? Here you also have 2 rows and 2 columns. So I write 2 by 1, and here I have 2 rows, 1 column, 2 by 1. That's it. So you may define matrix multiplication. And now look at this. We need to develop the theory of matrices, right? And we need to study system of linear equations. So we need to study the matrices A and B, right? The relation between A and B and so on. Because sometimes in reality we don't need to solve the system. Sometimes we just need to know how many solutions the system has. Is it right? And we need to develop the whole theory of matrices. Okay, and then that is about a half of the course of linear algebra. Of course, when you study matrices, you might think, yes, we have 3 cases, right? But how about an analog of A inverse? Because if A is not 0, so we might have an inverse, right, of a number. So you might think about A inverse, right? And we need to study different conditions for a matrix to be invertible, right? So that is about matrices. Now let's consider another point of view on the system of linear equations, right? The original system looks like x plus y equal to 1, 2x minus y equal to 3, and we discuss how to rewrite this system in the form of matrices. And we see, yeah, that is what? A, x equal to b, right? And we consider this as a generalization of the system of the equation ax equal to b. Okay. Right now, if we do another multiplication, let's look at this. What happened, right? If we separate x and y, so I would have the following one. I say, yeah, now I separate coefficients of x, so I have 1 and 2, right? And coefficient of y is 1, negative 1 in here. Okay, so since this is coefficient of x, I can write here x times 1, 2, and plus here I have y, and this is equal to 1, 3. How about that? We wrote this system, right, from the point of view of multiplication, from the point of view of matrix multiplication. We took the row in here and multiply with this column, and then the second row multiply with this column, right? And then that's what we have. But now you take some number x, right, multiply with some vector, the number y multiplied with this vector, you have another vector. So what does it mean? That means we try to express the vector 1, 3 as a linear combination of two vectors, 1, 2 and 1, -1. You see that? So, x and y are coefficients in this case, right? If we can solve the system, that means we can find x and y. So means we can express the vector 1, 3 as a linear combination of these two vectors. So that is another point of view on this system. You see this? Of course, they are equivalent, but I can read this system as I want to express this column as a linear combination of columns in here. Is that correct? So, when a system has more than two, or whatever they have, right? How many equations they have and how many variables they have, we will have a very general. So, general situations like, I have a vector, not only with two entries in here, right? You might have n entries, and you want to express some vector as a linear combination of all the vectors. Okay, that is very interesting problem, right? So express some vector in here as a linear combination of all the vectors, of the given vectors. And in that situation, we have to deal with vector spaces, right? And here we have different operations over vector spaces. So, and sometimes we study system of linear equation from this point of view. Sometimes you consider different problems, different questions in vector spaces using system of linear equations, and of course using matrices. Okay, so that is another part of this course. So we will study linear vector spaces, and then we study different operations over vector spaces. But that's not all. That is not all. Look at these two vectors, 1, 2 and 1, -1. Let me discuss this, right? These are vectors in R2. What does mean in R2? That means in the plane, right? In the plane. Look at this, why? Because we know if we have plane X or Y, right? Any point on this plane can be represented as a vector, right? Can be considered as a vector, because if you have A in here and B in here, so that is just a pair of numbers, A and B, right? So that is a vector, that is a point. And of course, if you remember, that is, complex numbers, right? Complex numbers, because, you can determine a complex numbers by a pair of real numbers. So you have a vector right here. And you know that, if A and B is an arbitrary vector, you can express as A 1, 0 plus B 0, 1. Why? Because, if you have 1 in here, right, and you have 1 in here, they are, we call unit vectors, right? Any vectors in the plane can be represented as a linear combination of these two vectors. And you can see that they are perpendicular. You see this? And this is very convenient representation, you see? Very convenient representation. Because, if you have coordinate A in here and B in here, you just, find the coefficient A and B. That's it. So if you have a vector, you try to express that vector as a linear combination of these two vectors, which are perpendicular and having length equal to 1. Okay, so it's very good. So let's go back to this problem. Yeah, you have vector 1, 3. You have another vectors 1, 2, and you have another vector is 1, negative 1, right? So you want to express this guy as a linear combination of these two guys. But you can see that actually these two guys do not have length equal to 1, right? And of course, if we draw that out, maybe they're not perpendicular. Okay, let's draw that out. Let's plot them on the plane, and we'll see. I have 1, 2. Where's 1, 2? This is 1. This is 2. Okay, so that is the first vector right here. The second vector is 1, negative 1. 1, negative 1 is right here. So I have the second vector. You see, they are not perpendicular, right? Where's 1, 3? 1, 3 is right here. So that is my vector. And I need to express this vector as a linear combination of these two guys. You see that? So if you compare this picture with this picture, you can see, yes, actually, the system 1, 0 and 0, 1 is much more convenient with this guy, right? They are not perpendicular, and they don't have the length equal to 1. So when you want to express some vector as a linear combination of these two guys, yes, we may have some difficulty. But the thing is, for this example, these two vectors, right, they are still good because you can represent any vector in the plane as a linear combination of those two vectors. So you need to deal with something like we call basics, right? Basics of a vector space. And then among bases, you need to choose a very good one like this, right? So we will learn how to do that. Agreed? But before that, we need to study the distance. We need to determine the angle between vectors like this, right? We have angle right here, 90 degrees. But this angle is not 90 degrees. So we need to determine, right, the angle between vectors. And then using that, you may find a basics, where, vectors are orthogonal, right? That's it, okay? And that is another part of this course. So it's just another point of view on a system of linear equation as, linear combinations of columns or of vectors right here. Does that make sense? Now, let's consider one more point of view on the system of linear equation. I think this may be very interesting to you. So, I write in here a x equal to b, right? Where a is some matrix. That's what we have seen, right? This is another matrix, but actually in this case we have vector, right? And here you have another vector. I hope you still remember that. Let me copy the system again, right? So the system looks like 1, 2, 1, negative 1 times xy equal to 1, 3. So what we are doing in here, in this case, if you look at this equation as a map or as a function, right? So what happened? I say, yes, I have some function a, right? And then if I have an input x in here, I will get an output b in here. This is input. Does that make sense? So, this is quite interesting, right? Or look at this. I have a box A in here, right? Some machine, right? I threw in this port some input X and I got some output B. So basically, that is another form of this system. In application, this is very important. So you may look at this picture as an evolution. What does it mean? That means here you have an old state and you want to get some new state in the future, right? So you need to decide what kind of old state would be in order to get B, okay? Or in other words, you may think, yeah, what does mean solving AX equal to B? That means you recover the X. Does that make sense? Because we have an input right here, right? And we want to get this output. We need to find X. We need to recover X from B. So that is some kind of inverse problem, right? From that point of view, okay? Inverse problem. Overall, in linear algebra, we focus on the system of linear equation AX plus B. But that is not all. We have different points of view on this system. So we will study how to solve this system. We will study matrix theory, different operations over matrices, right? We will study different spaces associated to matrices. Okay, and basically they are, vector spaces. And then we will study vector spaces with some distant functions. Okay, so I will write in here in the product spaces. And after that, we look at the matrix theory as the theory of linear transformations. And at the end, we will study different variants of matrices, like eigenvalues, eigenvectors, and how to use diagonalization in applications. You see, that is all about this course. So we have some picture already. So I hope that you enjoyed the video. Thank you for watching, and we'll see you in the next video.